Okay, good afternoon. How did lecture go Friday? Good? Great. Cool. We were busy having a big faculty shootout about whom to hire for next year. So, yeah, it's always terrible. Because, there are so many good people and we only get to hire like 2 of them. And so. Anyway, so we have a room for the final exam. It will be a week from this Friday, the 16th, 5 to 8 p.m. in 2050 VLSB. Yeah, which is, I think, much better than Hearst Gym, although not still perfect. This Friday is when we're doing the in-class course evaluation, so bring yourself physically to class and bring a pencil. Grades for project for the first half and homeworks 12 and 13 should be online today. I'm told only half the project grades are actually up as of yet, but today isn't over, so I still have some hope that we will meet the deadline. The complaint deadline for those grades is this Friday. So again, that's if you have a missing grade or you think the grade is inaccurate in some way, file a complaint using the online form by Friday. Okay, what we're doing this week, today and Wednesday, is looking at the last of the major programming paradigms that we're going to cover. I suppose really parallel ought to be on this list too, huh? Maybe I should put that down. Well, data parallel. Meaning the data is distributed among a bunch of computers, and they're all doing basically the same stuff on separate data. The last one is called logic programming or declarative programming, and we are not giving it nearly enough attention, but as with a lot of things in the lower division, the idea is to just let you know that this is a topic, and if it interests you, you can pursue it further. Okay, let's... Where do I want to be? Here's someplace, 4.4. Okay, load. CS61A lib query. Okay, so what we have here is an evaluator for a language that's very different from Scheme. We've been looking for the past few weeks at sort of Scheme variants, and also at Logo, which is on the surface in its appearance pretty different from Scheme, but in many ways is a close relative under the skin, in that procedure calling is the main organizing idea for doing everything in Logo as in Scheme. Today we're looking at something that's very different, a completely different paradigm, and so its interpreter is completely different, although we'll see that there's something that's like eval that takes something like an expression, but it doesn't actually produce a value. It does something a little different. So the way logic programming works is that up to now, when you write a program, what that means is that you provide an algorithm, a method, a recipe for coming up with a solution. In logic programming, we don't do that. Instead, we just tell the evaluator some things that we know, and then we can ask it questions. So for example, I can assert bang, Brian likes hot stickers. So I'm just putting in some assertions here. Okay? So now we know some facts. And now I can ask questions like, who likes pot stickers? And I get these two answers. So one big difference between what we've done so far and logic programming is that when you write a procedure, each procedure returns one value. Here, the result of a query can be many values, more than one. So I can say, Brian likes what? And by the way, the question mark before a word indicates that this is a variable. It's a little bit like the colon before a variable in Logo. So that word can be matched by anything. If I say, who likes cheese, I get no results. By the way, I have no idea whether Ramesh likes cheese or not, but if he does, it's not in the database. So that's one of the things you have to keep in the back of your mind here is that the system really only knows what you tell it. And if it doesn't know, it doesn't say anything. So I can't really logically ask the question, who doesn't like cheese? Because the database doesn't know for sure who doesn't like cheese. All it knows is that we didn't tell it about anybody liking cheese. So one more example. If I assert Brian likes ice cream, and now I ask Brian likes what? I don't get that result. So I asserted Brian likes ice cream and put it in the database, but Brian likes what doesn't match it. Why not? Well, I'm going to ask a different question. And now I do find it. So what's going on here is that pattern matching in this system works like if you remember when you wrote a version of equal question mark as an exercise. And basically the way your equal worked is if the things were numbers or words or something, it would just EQ compare them or equal sign compare them. But if the thing you're looking at is a pair, then you recursively ask, do the cars match and do the cooters match? So if I have a query like Brian likes, and here's my variable what, this can only match a list of 3 elements. Okay, so this language still has lists in it. It doesn't have procedures, we'll see, but it does have lists. And a pattern of the form Brian likes question mark what can't match Brian likes ice cream because that's a list of 4 elements. But that second pattern that I gave was Brian likes, and remember what dot means. What comes next is the cooter of this pair. So in the second case, the variable what is now part of the spine of this pattern. And it matches any number of elements, including 0, 1, 2, whatever. In the case of ice cream, it matched 2. Okay, so that's pattern matching. And that's basically the entire language. Almost. I left out one feature, which we'll get to in a minute. But right away, you're thinking, this isn't much in the way of primitive capabilities. It only knows how to do one thing, and that's pattern matching. So imagine if scheme only had equal question mark, or even if scheme had an extended version of equal question mark that could handle variables like this, but it didn't have anything else like car or plus or set bang or any of the if and so on. It seems like there isn't enough here to build a language that can do anything. But the amazing thing is that with one more addition, namely an analog to procedures that we'll see in a moment, this language really is universal. Any problem that can be solved by a computer can be solved within the confines of this system. So that's pretty cool. By the way, the patterns are just text. So I just typed in English sentences, and those work as patterns. But by convention, when we're teaching the system things, we don't do it this way. Instead, what we do is that the first word of an assertion is going to be the relation, that is to say, the verb that explains how the different pieces are connected together. So I would say something like this: assert bang likes Brian, and then I'd put ice cream in parentheses here. And assert bang likes Brian hot stickers. And now I can say likes Brian what? And I find out about both pot stickers and ice cream because now all the likes assertions are lists of 3 elements. So I can just fill slots, and if I have a 2-word name like ice cream, I just use a sentence, a sublist basically of the assertion for that slot. So this gives me a more uniform notation. I showed it to you first just typing in English sentences because I want to make the point that there's no mechanism behind these relations other than just pattern matching of text. So there isn't a procedure called likes someplace. They're just whatever assertions I put in the database. The system does not know that the relation names comes first. That's just something that makes it easier for a human being to understand the structure of things. And also, to be fair, it is used for efficiency because the way that this particular system stores the assertions is that they're kind of indexed by the first word. So all the assertions that start with the word likes are grouped together. And that makes it easier to find assertions if you have a great many of them in your database because when you're asking a question, the variables in your question are usually the noun slots. Who likes ice cream? Or Brian likes what? Rather than asking, what's the relationship between Brian and ice cream? That's a less usual question to ask. So just as an efficiency matter, it's good to have the relation first, but also just as a convention to help people understand the structure of the assertions in your database, we put the name of the relation first. Questions so far? All right. Oops. Yeah. Okay, so I just got back to STK by giving an illegal empty query because I want to say load, and I want to say, What I'm doing here in loading these files, by the way, sometimes people find this confusing in the demos. I'm cheating a little bit. This procedure that you see in the bottom half of the screen, AA, that's a scheme procedure that adds an assertion to the evaluator's database. So what comes after it in the file is a whole bunch of calls to AA with assertions. And, oops. Here they are. Here are the assertions. And it's as if I had typed into the query system, assert bang, mother of Dave is Ann, and so on. But the query system doesn't have an equivalent to Scheme's load command to get stuff out of a file. So it's easier if we just do the adding to the database in Scheme, in STK, that is, rather than in the query language. But just pretend I had said assert bang for all these things. So now I can ask questions like, mother of question mark child is Ann. And yet Beth and Dave. By the way, queries can have more than one variable. So going back to my original ones, I can ask who likes what, and I get results having to do with Brian and Ramesh and broccoli and pot stickers, and I still don't get ice cream because I didn't say dot. But that's just to make the point that you can have different variables. If a variable name appears twice, it has to match the same thing both times. So if I say, who likes who, I don't get any results at all. But, of course, the actual variable name is meaningful only to human beings, not to the system. So I can say, question mark X likes, let's put in the dot this time, question mark Y, and it doesn't matter that I said X and Y instead of who and what, I still get all these results. Okay? So now, we have this database about parenting, and let me just put up on the board what it says. The mother of Dave is Ann. Okay, so we have Terry, and Terry's child is Ann, and Ann and Mike have some children together. And Mike has a mother who's Mary, and their children are Dave and Beth. Okay. As a human being, we can draw a lot of inferences from this chart. This chart I got right out of the assertions that you see. If you look at the same time, it's going to be a little hard for the web people. If you look at the AA things on the screen up there, and if you look at this chart, I think you'll see that they're equivalent. But looking at the chart, we know things like that Terry is the grandmother of Beth, right? And that Dave is a sibling of Beth. Those aren't assertions in the database, and furthermore, we don't want to add them to the database. We could add a bazillion assertions. Terry is the grandmother of Dave. Terry's the grandmother of Beth. Mary's the grandmother of Dave. Mary's the grandmother of Beth. Dave is the sibling of Beth. Anne is the wife of Mike, and so on. I guess we don't know what sex these people are, so it would have to be Anne as the partner of Mike. Well, no, we do. We do know some of the sexes because in some cases we know that somebody is the mother of somebody or the father of somebody. It's really only Dave and Beth whose sex we don't know. Yeah, we could add information about that too. We could add assertions that say, you know, Dave is a guy, Beth's a woman, and all that. But I don't want to add all those assertions because if you imagine that Anne and Mike have another child, it wouldn't be good enough to add 2 assertions about that child's mother and father. In order to keep everything up to date, I would have to add 4 more sibling relations and 2 more grandparent relations as well. For human beings, we don't have to do that. You know, if I put Alfred down here next to Beth, you can figure out all those things. So we can do that too. We have rules. Like this rule. So that I can ask questions like, grandmother of who is Terry? By the way, these is things are just noise words for no particular reason. I didn't make up the example. And we find out that grandmother of Beth is Terry and grandmother of Dave is Terry. How did we know that? Because of this rule. This rule right here. So it said assert bang instead of AA quote. Assert bang. Rule. And a rule has a conclusion which comes first. The naming is a little counterintuitive. So this is the conclusion of the rule. Grandmother of GC is GM. GC for grandchild, GM for grandmother. And then comes the body of the rule, the same as a procedure has a body. And the body is this and thing. And is a keyword. There are 3 keywords in this language, and, or, and not, that have the obvious meanings, except we'll talk a little later about the non-obvious meaning of not. So, under what circumstances is somebody the grandmother of somebody? Well, we introduce a new variable parent here, and we say 2 things have to be true. First of all, GM, the person who's going to be the grandmother, has to be the mother of a new person, parent. And also, parent has to either be the mother of the grandchild or the father of the grandchild. So that's a rule. Now, is this rule a process for figuring out whether somebody is the grandparent of somebody? And does it say, for example, for every element in the database, for each lambda of assertion, blah, 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 database? No, it doesn't say that. It just says what the rule is. It's telling us a fact about the meaning, the definition of grandmotherhood. What does it mean to be a grandmother? Well, it means that you're the mother of the parent of the other person. And with this information, the query system knows how to use this rule along with the assertions in the database to find matches for a query like the one I made up on the top of the screen. So precisely how does this work? Remember that scheme procedure calling has 2 steps. So here's scheme. Well, actually, 3 steps. Step number 0 is evaluate subexpressions, right, because of applicative order. That doesn't apply here because there's no values in this system. There's nothing to evaluate. We're just doing text matching, words against words. So we don't have that step in the query system. Step 1 bind the parameters, the formal parameters to the argument variables. Right? So make a frame in which the parameters are associated with the argument values. The thing that corresponds to that here is try to match the conclusion of the rule and bind variables to text. So in order to see whether this rule is applicable, we go through the database. Well, no, I'm sorry, we don't go through the database. We take the query, which was grandmother of who is Terry, right? That was the question I asked. So we match that against the conclusion of the rule. The conclusion, well, so let's see. Let me get this exactly right. I said, grandmother of who is Terry. The conclusion of the rule is grandmother of question mark GC for grandchild is question mark GM for grandmother. So do these match? Yes. Grandmother of is equal to grandmother of. These are two variables. We don't know anything about them yet, so we just say they have to be the same. Is matches is. And now we know a value for grandmother. So the result of this match is that we say question mark GM is Terry. Question mark GC is question mark who. Okay? And now, step 2 is evaluate the body with those bindings. Step 2, similarly, evaluate the body as a query. Just as if I had typed it in at the query prompt, but constrained by those bindings. So we're only going to find matches for the body in which GM is Terry. And then what the scheme read eval print loop does is it gets back a result and prints it. What the query driver loop does, it doesn't get back a single result. It gets back, it turns out, a stream of frames. Each frame is a binding of names to values, variables to values. We have a bunch of them, potentially infinitely many. We'll see how that could happen in a bit. And what the driver loop does is for each frame that it gets, go back to the original query and figure out what values to plug into that query based on the frame, and then print out what we get. So we print out grandmother of question mark who is Terry, except the question mark who has been replaced by somebody or other who matched that. So there'll be, in this case, 2 different frames, one in which question mark who is Beth, and one in which it's Dave. Okay, question about the rules? So we can make more rules if we want. I can say assert bang, rule, sibling, question mark A, question mark B. So 2 people are siblings if or and mother of question mark A is parent. Mother of question mark B is parent. Oops. Hope I got this right. And father of question mark A is question mark parent. Father of question mark B is question mark parent. Okay, so let's see what siblings we have. Sibling question mark X question mark Y. So my rule wasn't very good. I did this on purpose. So what's wrong with this? Well, everybody is his or her own sibling. And we get the same result more than once. So I get Beth Dave twice, and I also get Dave Beth twice. It's not bad that I have both Beth Dave and Dave Beth. That should be, because we might have asked about them in either order, and we should get sort of symmetric results. But we shouldn't have the same person, and we shouldn't have the same result twice. And I could write a better rule that will take care of all that. But I'm not going to bother because I have something more important to show you, which is this. Load. Append. Here's how it works. Append A, B, C, D, E, what? It tells me. Well, how does that work? For reference, let me put up on the board here a scheme version of append. It says if null A, then B. So append the empty list to something gives the something. Otherwise, cons car A onto append could array B. Right? So that's defined in it's append in scheme. Now let's look at here's append in query system. And let me start with this second rule. It says append the empty list to anything gives anything. So, by the way, notice the difference, the first difference between a scheme function and a query system relation. Namely, the scheme function takes two arguments, which are the little lists, and it returns a value which is the big list. The relation, so to speak, takes three arguments, two little ones and one big one. And if you want, you can think of it as returning true or false. But it doesn't actually return anything, it just sort of succeeds or fails. In that respect, it's a little bit like the non-deterministic evaluator. It has this notion of succeeding or failing, although the implementation is very different. Okay, so This rule says append empty list anything, that anything is true, and that's like if A is null, then B is the same as the appended value. Questions about that rule? Okay, now for the fun part. This rule corresponds to the else clause in the append. So first thing to note is you can have more than one rule about this append relation. And if you think about it, that has to be true because I told you that there's nothing particularly special about being the first word of a matched list. So it's not as if the system knows that there's a relation called append. What it knows is that there's a rule about lists of length 4 whose first word is append. But there could be more than one such rule, and there is. So this is what we have instead of that if capability, is that we have as many rules as we want to have about the append relation. We only need 2 in this case. Something to note is that in Scheme, we're guaranteed that only one of these things happens. Because if evaluates this or it evaluates this, but not both. There's no guarantee like that in the query system. You could write rules in such a way that some particular question that you ask matches both rules. And that might be what you want, or it might not be what you want. So you have to think about that. Well, in our case, we want a rule that applies when the first little list is non-empty. And furthermore, we want to take its car and its cdr. But there aren't any functions in this system. So the most important thing to remember, the way to avoid getting 0 points on the question on the exam, is don't try to do composition of functions, because there aren't any functions. So for instance, don't say rule grandmother of grandmother grandchild. And let's say we have a parent rule. So we would say mother GM So this is an attempt to say that GM is the mother of the parent of GC. Yeah. Don't do that. Parent, suppose we write parent to mean mother or father, is not a function, it's a relation. It doesn't have a return value that can be part of a larger expression. So the only way we can build up expressions is with and, or, and not of relations that can be true or not true. Okay? So what we're doing here is this append rule says, okay, I want to make sure that my first list is non-empty, and furthermore, I want names for its car and its cdr. So in this program, question mark U is the car of A. Question mark B, or V, sorry, is the cdr of A. So this is query version, and this is the scheme version. And we still have, no we don't, I take it back. Yes, we do. We still have question mark Y is the same as B, in the scheme program. Notice that I didn't take car or cooter of B anywhere in the scheme program, so I don't need names for B's car and cooter, so I can just use question mark Y as the name for B. But A, I've made a pair, question mark U dot question mark V. So something dot something, that's the notation for a pair. Question mark U is the car, question mark V is the cooter. So everybody sees how this notation makes what I wrote on the board over there true. The question mark U is the car of A and question mark V is the cooter of A, yeah? With me? You're not with me. Who's with me? Okay, somebody who didn't stick their hand up, ask a question. Oh, dum. Okay, let me try to guess what's confusing people. What's confusing people is you've spent a whole semester learning a program in Scheme, which is a language that's procedural. The building blocks are procedures. And you're really, really accustomed to the idea of doing things by calling procedures. This is a pattern matching language. Basically, the only way we have to do anything is matching. And remember, what pattern matching means is it's just like that equal question mark that you wrote for homework back in chapter 2, except that if one of the things that you're looking at is a variable, it can match anything. Except that if you use the same variable twice, the matchings have to be consistent. Okay? So given that that's true, that all we have is pattern matching, if I have a specific case, maybe that'll help. If I take a specific case like append AB, CDE, what? Question mark U, okay, this whole thing, AB, has to match question mark U dot question mark V. This is a list. It's two pairs, right? This is a pair whose car is A and whose cooter is a pair whose car is B and whose cooter is the empty list. This is a pair, just one pair. Question mark U is the car, question mark V is the cooter. So question mark U has to be the car of this list, which is A. Question mark V has to be the cooter of this list, which is not just B, but list containing B, right? And question mark Y is CDE. And that's as far as I've gotten so far. We still have some more explaining to do, but are you with me now about this much? Yeah. Sorry? On the board above, it's a little confusing that I used A and B as just, pretend this as 1, 2, 3, 4, 5, if that helps. Those are the variables in the Scheme program. Okay? Yeah, I'm sorry, that was sort of bad of me. Pretend I said X and Y over here. Other questions? All right, moving on. So we've gotten past this first part, and we got past question mark Y. Now we're up to here. Well, if this first argument in the Scheme program is non-empty, what's the big list supposed to be? Well, it's cons something something. So it's a list it's a pair whose car is question mark U, and whose cooter is the answer to some recursive query, right? Some recursive procedure call, sorry. But I just told you over here that we don't have composition of functions in this language. So I can't write $U dot append something something, right? That's a no-no. So instead what I do is I say, okay, the car has to be $U, the first element of the first list. So that's something I know for sure. And I'm going to give a name to the result of that recursive append. I'm going to call it $Z. And then in the body of the rule, I'm going to say, what is $Z? It's the result of appending $V and $Y. So back over here in my example, what's the answer going to be? Well, it's going to be, we know what U is, it's A, right? So it's got to be A dot $Z, where $Z is the result of this query. Append V Y Z. Okay? So whatever the result of this is, namely, we know what the answer should be, B, C, D, E, that's going to be plugged into $Z. And so overall, we have A, B, C, D, E. Whew. Okay? So that's how this works. This example is in the textbook, so you can look over their explanation of it also. But I just want to show you now in the remaining few minutes, first of all, this is it. These two rules are the entire append program. Notice that there are no assertions in the database about appending. That is, there's no specific, like the ones for who likes what and who's the grandmother and the mother and father of what. There are no assertions to start with. There's just these rules. And the reason that that works, that we get any answers out, is that one of the rules is a base case rule that tells us what if the first little list is empty, what to do. Okay? So, I showed you that I can say, just as we could with the scheme program, what's the result of appending this list with that list? What's really, really cool about this pattern matching system and about relations as opposed to functions is that you can, so to speak, run them backwards. I can say append AB what to get A, B, C, D, E, and get an answer to that. I can say append what to C, D, E to get A, B, C, D, E. It can figure that out. And finally, I can say append this, that, A, B, C, D, E. How many answers are there?
5,
Nope. Only 6. 6 answers. Right? These are all the possible appendings of two lists that give the answer A, B, C, D, E. I think that's pretty amazing. So this is what you should sort of take away with you today, is that this query system, the rules that we put in really are nothing but this scheme procedure in a different notation. But the evaluation technique that goes along with that different notation is smart enough to be able to run the algorithm backwards, because it isn't an algorithm. The rule does not say, first do this, then do this, then do this. It says, here's some things that I know about appending two lists. I know that if the first list is empty, then the result is the same as the second list. And I know that if the first list isn't empty, then the result starts with the car of the first list and goes on to be the appending of two other things. And it says what the two other things are. And with only that information, I can do this magical result of getting 6 different possible bindings for the variables this and that, which are all of the possible ways of doing it. And on that, we will leave until next time, when we see how it really works.